So as we're discussing acids and bases, we're going to have to talk about the pH scale. And to just explain what the pH scale is about and how we actually determine the numbers in the pH scale, I want to consider again this reaction that we looked at in class Thursday. And what will stand out to you from the reaction is I pointed out that this H3O that with a positive charge is called the hydronium ion. And so that's what happens as you mix an acid with water, you'll get this hydronium ion. And so the pH scale is actually based on the presence of this hydronium ion. That's how the numbers are determined in the pH scale. So the pH scale will tell us how acidic a solution is or how basic it is, depending on the presence of this hydronium ion. All right, so pH scale runs basically, if you think of it as a number line, it runs from 0 to 14. And right in the middle here, where you have 7, that's what we call neutral. Or if you see, you may see a product in the store that's called pH balance. And by the way, I don't think I said pH stands for potential hydrogen, okay? But it's like I said, it's a measure of the amount of this hydronium ion. So pH balance is right in the middle. It's neither basic nor acidic. On this side, you have the acidic side of the scale. So anything less than 7 is considered acidic. And the more that you go, the closer you get to 0, the more acidic the solution is considered. This is the basic end of the scale, right? And the closer you get to 14, the more basic a substance is. All right, so 0 to 14, closer to 14, basic, closer to 0, acidic. 7 is the neutral area right in the middle. That's pH balance. All right, so that's all I really want to make sure that you know about the pH scale. If you want to see an example of some substances and kind of where they fall on the pH scale, there's a nice chart, a nice diagram on page 338, not a chart, but a diagram, a drawing of the pH scale, and it's got some common household items, some substances that are listed there so you can see where they fall on the scale. All right, so having talked about pH scale, let's move on to our next topic. Because acids and bases are basically, I keep saying basically, and it's not a good term to use when we're talking about acids and bases. Because acids and bases are, in essence, chemically opposite of one another, you can have, they can cancel one another out, right, in a chemical equation. And so we would say a base would neutralize a particular acid, all right? So in order for this to work, if you want the acid to be fully neutralized, then you want to make sure that that you have the exact amount of the base in order to match the particular amount of acid, or vice versa, right? You want to make sure if you're trying to make sure all the base is eliminated, then you got to have just enough acid to eliminate that with nothing left over. Okay, so let's do some examples of how you might go about doing that. The first example is on page 341, example 11.4, and it says a chemist would like to neutralize a 3.4 molarity solution of HBr. If there are 312 milliliters of the solution, what volume of a 2.0 molarity NaOH solution, sodium hydroxide solution, would have to be used? Okay, so let's just write down what we know. 3.4 molarity solution of HBr, and we've got 312 milliliters of that solution. What volume of a 2.0 molarity solution of NaOH do we need? All right, so just to understand this problem here, we're given the molarity, and we're given the volume, the molarity of the solution. We're given the volume of that solution. Given the molarity of another solution, and we want to find the volume of that solution. What volume of this solution, what volume of this base will neutralize entirely this acid? Okay, so the first thing that we have to do is we have to write out the reaction. We learned how to do that in class yesterday. So HBr plus NaOH, HBr being our acid, right? This is our acid. This is our base. Why do we know that's the case? Remember from yesterday, Thursday, that this is a covalent compound that begins with H, and this is an ionic compound that has the hydroxide ion in it. So that was one of the things that we saw in our kind of three identifiers when you're trying to figure out which one's the acid and which one's the base in a chemical equation. That's one of the ways that we can identify those guys, a couple of the ways. And when you combine this acid with an ionic base, what happens? We get water and we get a salt, right? In this case, so the salt's whatever's left over when this H combines with the OH over here. And so we've got NaBr. We looked that up in our periodic table, and we see that Na is in column 1, and we see that Br is in column 7. So the Na then is going to have a 1 plus charge. The Br is going to have a 1 negative charge, and so when we swap and drop, we're left with NaBr. So that's the substance here. So the only other thing we have to do now is just make sure our equation is balanced. And as it turns out, this one is. We don't have to do any further balancing. We've got 2 H's on this side, 2 H's here, 1 Br, 1 Br, 1 Na, 1 Na, and 1 O, and 1 O. So we're already balanced. So the next step is we're going to use some, we basically need to, in order to figure out how much of NaOH we need to completely neutralize this acid, we need to find out how many moles of this acid we have, and then using stoichiometry, we can figure out how many moles of the base that we need. So how are we going to get the number of moles of HBr? Well, we do that with the molarity, because we know that molarity, if you remember, molarity equals moles of solute over liters of solution, right? So what do we have here? We have the moles, we have the molarity of our solution, and then we have the liters of the solution. So we actually have it in milliliters. We need to convert that to liters, so that's going to be 3.312 liters. But knowing those things, we can figure out the number of moles of HBr by multiplying molarity times the liters of the solution, right? That's just the algebra that we need to do in order to rearrange this equation and solve for the number of moles. All right, so let's do that. So that equation there tells us that the number of moles, right, the number of moles of HBr is going to be equal to, let's go ahead and let's write it like that. Moles of HBr is equal to the molarity, which is 3.4, times the volume, which is 0.312 liters. And so that's going to give us a value of 1.1 moles. 1.1 moles of HBr. All right, so how much NaOH do we need? Well, we just use stoichiometry to convert this from moles of HBr to moles of NaOH. And how do we do that? Well, we know this. You guys already know the answer, right? HBr, we multiply that time. We know that 1 mole of NaOH, because of the understood 1 in front of that compound, is equal to 1 mole, the understood mole number in front of HBr. So there's a 1-to-1 relationship. So if we have 1.1 moles of HBr, we need 1.1 moles of NaOH. All right? The problem, though, didn't ask us for the number of moles of NaOH. It asked us for the volume of a 2.0 molarity solution of NaOH. So again, we go back to the definition of molarity, which is M equals moles over liters of solution, right? And so solving for liters here, we would get liters equals moles over molarity. So the liters of the solution is going to be the number of moles, which is 1.1 mole, which we calculated here, divided by the molarity, which was given as 2.0 molarity. And so we do that Punch that in our calculator and we get 0.55 liters. All right, so this is our answer. 0.55 liter solution of NaOH is what we need. You could convert that to milliliters since this HBr solution was given in milliliters if you want to. If you were to give me 550 milliliters as your answer, that would be correct as well. Okay? But since the problem didn't specify which unit it wanted it in, then liters would have been fine also. Okay, let's do another problem which is almost identical, but it changes a little bit at the end of the problem. That's problem 11.5. Example 11.5 in your book. And example 11.5 says, your stomach produces hydrochloric acid, which is HCl, that is used in the digestion of food. Sometimes, however, it overproduces HCl. Antacid tablets are meant to neutralize the excess HCl that comes from the overproduction. So when we take in antacids, that's what's happening. It's a neutralization reaction, right? We're trying to provide enough of a base to neutralize the excess HCl that's in our stomach. So if a stomach overproduces 84 milliliters of a 0.10 molarity HCl solution, so 84 milliliters and 0.10 molarity, that's HCl. How many grams of MgOH2, which is an active ingredient in some antacids, would be necessary to neutralize it? So we're looking for grams of MgOH, magnesium hydroxide, MgOH2. All right, hydrochloric acid combined with magnesium hydroxide. So let's do our chemical equation just like we did before, and then we have to make sure that it's balanced. Again, we've got an acid combined with an ionic base, so it's going to produce water and the salt. And in this case, when we get rid of the H and the OHs, we're left with MgCl. Now Mg is in column 2A, so it's going to have a 2+ charge. Cl is in column 1A, so we swap and drop here, and we're left with MgCl2. All right, so that's the salt that's produced over here, MgCl2. All right. So now let's balance it. We see we've got 2 Cl's here, right? So we're going to have to put a 2 in front of this. We also have, let's see, we got 1 Mg, so that's fine. But we have 2 O's here, right? So we know we're going to need a 2 in front of this. And so Cl's are correct, Mg's are correct, O's are correct. Let's check our H's. 2 H's here, 2 H's here for a total of 4 on this side. 2 times 2 here is 4 H's on that side, right? So our equation's balanced. So just like we did before, right? If molarity equals moles over liters, then we can find out the number of moles by multiplying molarity times liters. And here, we said we were given that we had 84 milliliters. 84. And so let's, molarity was 0.1 molarity times 84 would be 0.084 liters. Because remember, we have to do this in liters. And so that's going to give us a value of 0.0084. Yeah, I should have known that. 0.0084 moles of what? Of HCl. All right. So then how many moles of MgOH2 do we need so that we have just enough for the reaction to take place so that all the reactants are used up? Using stoichiometry, we say that 0.0084 moles of HCl, we can convert that to moles of MgOH2 because we know that 1 mole of Mg, why did I do a little M? I don't know why my brain does that sometimes. All right, oh, that's why. Yeah, Mr. Walker's losing it. All right, 1 mole of MgOH2 over 2 moles of HCl. And so that's going to give us the number of moles of MgOH2, and that calculation gives us 0.0042 moles of MgOH2. Now, it didn't ask us for moles of MgOH2. It said how many grams of MgOH2. But we know how to do that. We can just use the atomic mass, right, of MgOH2. We go to our periodic table. We figure out the atomic mass of that. And that tells us that 1 mole, when we do that calculation, it tells us that 1 mole of MgOH2 is equal to 58.33 grams. So for every mole of MgOH2, we'll have 58.33 grams. So that will allow us to calculate, to convert 0.0042 moles of MgOH2 to grams. Using this relationship, we know that we'll have 58.33 grams if we have 1 mole. And so our final answer then is going to be 0.24 grams of MgOH2. So it's basically the same stoichiometry problems that we've been doing before. We just have to, make sure that we remember the definition of molarity, so we can convert when we're given molarity instead of the number of moles. As long as we're given the number of liters and the molarity of the solution, we can calculate the number of moles and then of one substance, and from that we can get the number of moles of the other substance. And then we can either convert to grams like we did here, or we could convert to liters if we know what molarity they want the solution to be that'll neutralize the other one. Okay? All right, so I'll see you guys in the next lecture. All right, so we want to talk about acid-base titrations next. And first I want to define the term anthocyanins. Anthocyanins are natural pH indicators. They are chemicals that will change color in the presence of acids and bases. And so the reason we're mentioning anthocyanins is because they can be used in acid-base titrations. What is an acid-base titration? Well, that's the process of taking an acid of known concentration and adding a base of unknown concentration, or vice versa. You could start with a base and add an acid of unknown concentration. But you know the concentration of the first, you don't know the concentration of the other one, and you add the other substance until a neutral pH is reached. And this, we call this the endpoint. So what we've done then, when it reaches this neutral pH, we can determine the unknown concentration. How do we know when it's reached a neutral pH? Well, you could use something like an anthocyanin so that when it turns to a particular color, we can identify the point at which things are neutral. So you would have this known concentration of an acid. You add the anthocyanins in with that, and then you keep adding the base until it changes the color, identifying that it's reached a neutral pH. And from that, you can determine the concentration of the base. So this is much easier to see if we just do an example. But if you'll go to the page where the example is, which is on page 344, you'll also see the device that's usually used in acid-base titrations, the burette that's there on the left. And so you can see how you're starting, you got a certain amount of, we've got the acid down in the beaker, and you've got the base that's above it that we're slowly, dripping down into the beaker, or actually into the Erlenmeyer flask. But we drip it down in there because it's in a device that allows us to measure the volume that was used. We just keep adding it until we see the color change that we're looking for, and then we know what volume we used, and from that we can determine the concentration of the base that we were adding to the acid. So let's do problem 11.6, which is an acid-base titration problem. And it says this. It says 125 milliliters of a NaOH solution of unknown concentration is titrated against a 1.29 molarity solution of HCl. It takes 12.11 milliliters of acid to reach the endpoint. What is the concentration of the NaOH solution? All right, so 125 milliliters of NaOH unknown concentration. And what do we say when we say concentration? What do we mean? We mean unknown molarity, right? So unknown M, and we have a 1.29 molarity solution of hydrochloric acid, HCl. And 12.11 milliliters of this HCl solution is what gives us our endpoint. And so what is the concentration? What is this molarity for the NaOH? So just like before in our last example, we're going to write down the reaction and make sure it's balanced. HCl plus NaOH is going to yield water plus a salt. We're not going to go through these steps because this is exactly the problem we did in the last video, the first problem that we did. So it's already balanced. And so what are we going to try to find out first? Well, first we need to determine the number of moles from this, right? Molarity, again, equals moles per liter. And so we can get moles by multiplying the molarity, which is 1.29 in this case, times the liters of the solution, which is going to be 0.01211, converting that to liters. And so we have 0.0156 moles of HCl, right? Now, how many moles then of NaOH is that going to be? This is a 1-to-1 relationship because for every 1 mole of HCl, we have 1 mole of NaOH. And so we know then that we have 0.0156 moles of NaOH also when the solution is neutralized, right? When the combination of this acid and base becomes neutral, has a pH of 7. And so the question though is, what's the molarity of the NaOH if we have 125 milliliters of NaOH? And we're going to use this equation again, right? So molarity equals moles of solute, which we determined to be 0.0156 moles, over liters of solution, which they've given us to be 0.125 liters, just converted that in our head from milliliters to liters. And so that's going to give us 0.125 molarity, a 0.125 molarity solution of NaOH. Okay? It's really the exact same problem that we've already done. It's just at the end of this one, instead of trying to determine, on our last problem we had to determine the liters of solution in the first problem. In the second problem, we had to determine the grams of the base. This time, we're having to determine what the molarity of the base was, because that was unknown at the beginning of the problem. But those problems are all almost identical, right? The beginning of the problem is exactly the same. It just changes slightly at the end here, depending on what they're asking us for. All right? Okay, so our last discussion for this chapter is the diluting of acids and bases. We want to consider that because a chemist might buy a certain amount of acid or base, but they buy it in a concentrated form, right? But for a particular experiment, you don't need it that concentrated. So you're going to have to dilute the concentrated amount that you got to get the molarity of solution desired for whatever your particular purpose is, whatever the chemical reaction is that you're trying to achieve. All right, so let's do an example to understand how this works, and it's example 11.7. And it says that concentrated hydrochloric acid is bought from a chemical supply house that has a 12.4 molarity solution, right, of HCl. If a chemist needs 200, but that's not what the chemist needs, right? The chemist needs 250 milliliters of a 2.5 molarity solution of HCl. So how should she prepare it? So how do you take this 12.4 molarity solution and get from that the 2.5 molarity solution? Now it should be obvious that because this is a higher number here, that the hydrochloric acid is a higher concentration in this solution than it is in the desired solution, right? So what are we going to do? We're going to add enough water to dilute this concentrated solution down so that we end up with this molarity of solution. This is actually a really easy problem. And so the first thing we're going to have to again remember is that the molarity of a solution is the number of moles of the solute divided by the liters of the entire solution, okay? And so knowing that that's the case, we can calculate the number of moles, the desired number of moles of HCl in this diluted solution, right? So the moles are equal to the molarity of the solution, which is given to be 2.5. That's what we want, is a 2.5 molarity solution. And 250 milliliters of that. And so let's convert that to liters. That's going to be 0.25 liters, right? So that's the value that we need here. All right, so that's going to give us our number of moles, which is 0.625 moles of HCl. That's what we want, right? We want 0.625 moles of HCl. So how do we dilute this down so that we can have 250 milliliters of solution that has exactly 0.625 moles of HCl in it? All right. So if we have a 12.4 molarity solution, and we want to determine, and we know that we want in that solution 0.625 moles, then how many liters of that solution do we need to make sure that we have 0.625 moles, right? So we solve for L here. So L is going to be equal to 0.625 moles divided by 12.4 molarity, and that's going to give us 0.0504 liters of solution. That's our total solution, right? So that's how many liters of this solution that we have to have so that we get 0.625 moles, right? Is that the final answer? That is not the final answer, because once we pour out 0.0504 liters of this solution, or we can convert that and say that that's 50.4 milliliters, right? When we pour out 50.4 milliliters of that solution, that gives us the right number of moles, but we need 250 milliliters of our solution. And so what we basically have to do then is add enough water to this so that it equals 250 milliliters, right? So we just take 50.4 milliliters of the original solution, 50.4 milliliters of the original solution, and we add to that, let's see. Well, they don't actually ask us to write that down, plus enough water to equal 250 milliliters, right? Well, what was the actual question? How should she prepare? Okay, so that's what we would do. We would pour out 50.4 milliliters of the 12.4 molarity solution, and then we would add enough water to equal 250 milliliters. So I hope that makes sense to you what we just did, right? We had a high concentration. We had a hydrochloric acid solution that was a high concentration, and if we had poured out 250 milliliters of this solution here, we would have had way too many moles of hydrochloric acid. How many moles of hydrochloric acid did we need? Well, we figured that out based on these values here. We calculated the number of moles that we needed. And so once we calculated the number of moles, then we could figure out how much of this solution we needed to get that many moles. Remember, moles is just the number of something, right? It's just a certain number of those hydrochloric acid molecules, right? And so once we got the number of moles of that in a solution, and we knew that the volume of that was 50.4 milliliters. We just had to add enough water. We don't want to add any more hydrochloric acid because then we'll have too many moles. But if we add just water, we'll maintain the number of moles of hydrochloric acid. And so we added enough water to equal the 250 milliliters that the problem asked for. And we're done. All right, so that's the end of chapter 11. As always, you guys let me know if you have any questions, and I will see you, Lord willing, in a couple of weeks. Have a good one.